Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So imagine you are designing a multi-million-dollar, high-performance aerospace gearbox. You spend, months running these absolutely perfect simulations in your CAD software.
Right. The math is totally flawless.
Exactly. Flawless math. But then, during the very first full-load physical test, within maybe 5 minutes, the gears just tear themselves to shreds. I mean, the metal scores, the bearing seize up, and the entire system violently self-destructs.
And the craziest part is the culprit wasn't your math at all.
No, it was literally a mechanic on the floor who tightened a single casing bolt in the wrong sequence. So today we are really pulling back the curtain on the high-stakes, deeply unforgiving world of custom gearbox design.
Because that specific failure scenario, it's actually incredibly common. Designing gearboxes is often viewed from the outside as this kind of dark art. You know, people look at a transmission and they just see mechanical alchemy.
Yeah, like it's just a black box of magic.
Right. But the reality is there is absolutely no magic inside that metal casing. It is pure, unadulterated, applied mechanics. By following a rigorous, unyielding step-by-step process that's grounded entirely in basic physics and geometry, any listener who understands the fundamentals can absolutely master this. I mean, a gearbox is really just a translator, converting the language of speed into the language of torque and vice versa.
I love that. A translator for torque. So our mission today is to build a mental workbench for you, the listener. We are walking you through the end-to-end engineering of a highly specific, very demanding custom motion project.
And it's a fun one.
Oh, it's a beast. The scenario demands 3 distinct mechanical feats from a single overarching system. First, you need to calculate the actual human hand force required to move a 5-ton piece of heavy equipment down a linear rail.
Which is no small task.
Not at all. Second, when horizontal motion isn't enough, you have to use that exact same gear train to lift that massive equipment vertically against the relentless pull of gravity.
Right, fighting gravity changes everything.
And finally, you need to engineer a mechanism to lift a massive plug and rotate, basically index it precisely out of the way, stopping on a dime without shattering the drive shaft.
It really represents a classic, comprehensive mechanical puzzle. We're dealing with linear force, we've got multiplied rotational torque, fail-safe gravity braking, and intermittent kinematic motion.
Okay, let's unpack this. We have to start with the blueprint phase, the 6-step gear design process that's outlined in our source material. Because skipping even a fraction of a step here doesn't just mean you get a less efficient machine, right?
Oh, no. It usually guarantees a very expensive, potentially dangerous mechanical failure. You can't skip ahead. So the very first step is to determine loads and speeds.
Which sounds obvious.
It does, and people usually begin by analyzing the prime mover nameplate. Like,
Right.
What does the motor say it can do? But the nameplate only tells you the steady-state operating parameters.
Yeah.
You have to dive deeply into the actual duty cycle.
Like how often it starts and stops.
Exactly. A gearbox that runs continuously at a steady speed experiences drastically different internal stresses than one subjected to, constant starting, stopping, and violent reversing. You are actively looking for external shock loads that the prime mover will transmit straight through the teeth of your gears.
Wow, okay. Which leads right into the physical architecture.
Yeah.
Because once you know the violence of the loads you're dealing with, step 2 is determine gear type.
Yes. This is where you decide the physical arrangement of the actual shafts.
Like parallel versus crossed.
Right. Parallel shafts give you one specific set of efficiencies. But if your machine footprint forces you into a crossed axis setup, you completely change the friction dynamics. And you drastically change the noise profile of the entire transmission.
Which I guess forces your hand on step 3, right? Material and heat treatment.
It absolutely dictates it. If you're forced into a cross-axis worm gear situation, for instance, you're suddenly dealing with immense sliding friction. Your material choice is no longer just about raw yield strength.
It's about surviving the scrape.
Exactly. It becomes this brutal balancing act between surface wear resistance and core toughness. You might need a gear with a glass, hard, carburized exterior just to survive the sliding wear.
But the inside still needs to be soft.
Yeah, a relatively soft, ductile core to absorb those shock loads we talked about without shattering like glass.
That makes a lot of sense. And then the operating speeds dictate step 4, which is determine quality needed. I mean, a low-speed agricultural gearbox can probably tolerate some minor manufacturing vibrations, right?
Yeah, a tractor gearbox is pretty forgiving. But if we are designing a high-speed turbine reduction gear, The vibration tolerances shrink to fractions of a thousandth of an inch. And the quality level dictates the machining methods, which, drives the cost exponentially.
So then step 5 brings us to the basic design.
Right. This is where we look at the raw space available in the machine envelope and map that against standardized tooling. You never, ever want to design a custom gear tooth profile if a standard, easily manufactured profile will do the job.
Keep it standard if you can.
Always. And finally, step 6 is the detail design. That's where we run the intense stress analysis on the tooth roots, determine the raw material form, like whether we are casting, forging, or machining straight from a billet, and optimize the entire assembly for actual manufacturing.
So I want to pause and drill down into step 5 for a second, the basic design. Because for the design junkies listening who are, dusting off their drafting tables or firing up their CAD suites, we really need to establish the fundamental vocabulary of the physical gear itself. The source material refers to this as the ABCs of gears.
It's a great term for it. The entire foundation of basic design rests on how we define and measure the physical size of a gear tooth. And because engineering is a completely global discipline, you really have to be fluent in 2 completely different dimensional languages.
The metric versus imperial divine.
Exactly. Internationally, operating under ISO standards, the physical size of a gear tooth is defined by the module, which is denoted by the lowercase letter m.
Okay, lowercase m.
Right. The module is fundamentally tied to the metric system. It is a direct ratio of the gear's reference diameter in millimeters divided by the number of teeth.
But if you are working on legacy systems, or you're deeply entrenched in the aerospace and defense sectors in the US or the UK, you aren't using module. You are looking at the diametral pitch, right? DP.
Yes, DP. And rather than being a direct measurement of physical size like the module, diametral pitch is a ratio representing the number of teeth per inch of pitch diameter.
Which means it's backwards, basically.
It is an inverse relationship, yeah. A larger DP actually means smaller, finer teeth.
That always trips people up. So what's the bridge between the two?
The mathematical bridge between these 2 global standards is a rigid constant. The module equals exactly 25.4 divided by the diametral pitch.
Okay, so if my drawing calls for a diametral pitch of 8,
then your metric module is 25.4 divided by 8, which yields a module of exactly 3.175.
Yeah.
And once you understand the tooth size, you have to determine the circular pitch, denoted by a lowercase p.
The circular pitch is the actual physical arc distance, right? Like along the pitch circle from a point on one tooth to the exact corresponding point on the adjacent tooth.
Exactly. It's the physical spacing. To calculate the circular pitch, you simply multiply pi by the module.
Well, simple enough.
Yeah. And that physical arc distance dictates how thick the tooth can be, and crucially, how much space must be left open for the mating tooth to actually enter the gap.
Right, they have to mesh. Okay, so we have the size and the spacing. But the defining characteristic of modern high-power transmission is the leaning angle of the tooth itself. The geometry of how one tooth actually strikes another is governed by the pressure angle.
The pressure angle is everything. It's the primary element dictating the tooth profile's shape. You can think of it as the angle of attack. The modern near-universal standard for the pressure angle is 20 degrees.
Why 20 degrees specifically?
Because it provides a wide, incredibly robust base at the root of the tooth. That maximizes load capacity and physically prevents the tooth from snapping off under heavy shock loads.
But the sources are really careful to point out that 14.5 degrees used to be super prevalent, right?
Very prevalent, yes. If a listener is rebuilding a legacy gearbox from, say, the mid-20th century, they are absolutely going to encounter that steeper 14.5 degree angle.
Did it have any advantages?
Well, it ran quieter, but the teeth had a much narrower, weaker base. And you absolutely cannot mix a 20-degree gear with a 14.5-degree gear.
They will mesh.
Oh, they'll touch, but they will physically destroy each other under load.
Yikes. Okay, good to know. And the final piece of the basic vocabulary is the center distance. When you finally mesh 2 gears together, their theoretical pitch circles those invisible cylinders that represent their pure rolling action. They must be perfectly tangent.
Perfectly touching, yes. And the center distance is calculated geometrically as half the sum total of their reference diameters.
And that precise geometry brings us to the most vital foundational concept in the entire field of kinematics. It's a term that sounds almost, grammatical. But in mechanics, it is the absolute law of the universe. Conjugated action.
Yes. Conjugated action is the fundamental law of gearing, period. This law dictates that gear teeth must be shaped to produce a flawlessly constant angular velocity ratio.
Meaning no speeding up or slowing down.
Exactly. As the driving tooth pushes the driven tooth, the actual point of contact travels. If the velocity ratio fluctuates even by a tiny fraction of a percent during that transfer of power, the driven gear speeds up and slows down microscopic amounts, thousands of times a minute.
And that fluctuation isn't just a math problem, right? It translates directly into physical violence inside the casing.
Total violence. The gears vibrate, they scream with this awful high-frequency noise, the lubrication film completely breaks down and the metal rapidly wears away. The teeth must push against each other in a way that perfectly mimics two perfectly smooth, frictionless cylinders just rolling against one another without any slipping whatsoever.
So how do you actually achieve that? You can't just use, like, triangles or trapezoids for the teeth.
No, absolutely not. Achieving that constant velocity requires incredibly specific geometry. Historically, like back in the day, clockmakers achieved this using the cycloid profile.
Did that work?
It worked beautifully, actually, but it was incredibly sensitive to the center distance. If the distance between the gears shifted even slightly, like due to heat or where the conjugated action was totally destroyed, today, the undisputed king of gear geometry is the involute curve.
I love the involute curve. The beauty of it is its forgiveness, right? Like
Yeah.
you picture unwinding a taut string from a cylinder. The end of that string traces through the air. That's an involute curve.
That's the exact perfect visualization for it.
And when you shape gear teeth using that specific mathematical path, you gain a massive mechanical advantage. Because if the center distance between the gears varies slightly, maybe the casing expands as the oil heats up, or the manufacturing tolerances are just slightly loose, the involute profiles still push against each other with a perfectly constant angular velocity ratio.
Right. It is a brilliantly forgiving geometry operating in an entirely unforgiving mechanical environment. It literally absorbs the chaotic reality of thermal expansion and bearing wear without losing the fundamental law of gearing.
Okay, so our foundation is solid. We understand the loads, the modules, the 20-degree pressure angles, and the absolute necessity of the involute curve. Now, we have to apply that transmission to the first physical challenge in our custom motion scenario.
The heavy equipment.
Yes, we have a 10,000-pound piece of heavy equipment. We need to move it down a linear rail, and we need to calculate the actual physical human hand force required on a crank handle to make that happen.
Right. So before we can even calculate the human effort, we have to engineer the interface between the machine and the ground itself. We have to size the track wheels and the linear rail using the empirical data provided by the machinery's handbook.
Because 5 tons is no joke.
It's massive. We are dealing with a 10,000-pound point load bearing down on a very, very small contact patch. The material properties of the wheel and the rail dictate absolutely everything here, specifically a material constant denoted as K.
And the source data gives us two starkly different options for our wheels. If we cast the wheels from iron, the K constant is between 300 and 400. But if we use cast steel, the K constant leaps to somewhere between 600 and 800.
Right, it essentially doubles. And we have to look at the metallurgy to understand why cast steel can handle roughly twice the concentrated load.
What's the difference at the microscopic level?
Well, cast iron is essentially riddled with microscopic graphite flakes, which makes the material very rigid, sure, but also incredibly brittle. Under a massive 10,000-pound point load, those graphite flakes act as internal stress concentrators.
Oh, so it just cracks.
Exactly. The material will pit, spall, and eventually just shatter. Cast steel, on the other hand, has a dense, highly organized crystalline structure. It has the toughness to distribute that massive concentrated load across the contact patch without any microscopic fracturing.
So for our 5-ton equipment, we are absolutely specifying cast steel to take advantage of that 600 to 800 material constant. Now we run the machinery's handbook formulas to determine the actual physical dimensions. We have a 10,000-pound wheel load resting on a cast steel rail.
Right, so the specific mathematical derivation for the required rail width under these conditions is calculated as 0.4 plus 5 divided by 8 inches.
And when you run that math,
When you execute it, it dictates a minimum required rail width of exactly 1.025 inches.
that's wild. We have a rail just over an inch wide supporting 5 tons per wheel. The metallurgy is doing a massive amount of heavy lifting there. But what about the diameter of the wheel itself? If the wheels are too small, doesn't the contact patch shrink?
It shrinks drastically, and then the pressure skyrockets, and the cast steel wheel simply digs a trench right into the rail.
Like a pizza cutter.
Exactly like a pizza cutter. So we verify the geometry using a secondary formula that balances the 10,000-pound load against the 1.025-inch rail width and the cast steel K constant. The results prove that a 20-inch diameter wheel provides a large enough arc to safely carry the load.
So the 20-inch diameter spreads the contact patch just enough to prevent the wheel face from deforming the track. Awesome. The track is laid. We have 20-inch cast steel wheels sitting on a 1.025-inch track. The 5-ton load is fully supported. But here is where the rubber meets the road, or, well, the steel meets the steel. The design requires a human being to physically move this mass using a hand crank connected to a screw mechanism. So how hard do I actually have to push that handle?
We are entering the realm of mechanical advantage now, translating rotational human effort into immense linear force. We have to clearly define the variables in our mechanical ledger first.
Lay them out for us.
Okay, capital F is the force applied at the very end of the crank handle. This is the physical human effort in pounds. Capital R is the lever arm, which is the physical length of that crank handle. Lowercase r is the pitch radius of the drive screw itself.
Okay, got F, capital R, lowercase r.
Then lowercase p is the lead of the thread, the precise linear distance the screw advances in one complete 360-degree rotation. Capital Q is the massive 10,000-pound load. And finally, mu, which is the coefficient of friction.
So if we were operating in a vacuum with perfectly frictionless surfaces, the math tells a very simple story of leverage, right? The force F would equal the massive load Q multiplied by the thread-led lowercase p, all divided by the circumference of the crank's rotation.
Which is 2 times pi, or roughly 6.2832, multiplied by the crank length capital R.
Right, and that frictionless equation shows the pure beauty of Archimedes' lever. By making the crank handle longer, or by making the screw threads finer and closer together, you can move almost infinite weight with very little force.
It's beautiful on paper. But, we aren't in a vacuum. We have heavy steel threads grinding against heavy steel nuts under 5 tons of pressure. Friction changes the entire mechanical ledger. It acts as an unavoidable tax on the human operator's muscles.
A friction tax, I like that.
It's exactly what it is. Friction radically complicates the math, and its effect depends entirely on the direction of motion. We actually must separate the kinematics into 2 distinct scenarios here: motion that assists the load and motion that resists the load.
And pushing it down a flat rail is resisting.
Right. When we are fighting the load and fighting friction simultaneously, the coefficient mu weaves its way through the entire equation. The human force F becomes the load Q, multiplied by a very complex numerator.
Let's conceptualize that complex numerator without getting bogged down in reading raw algebra, because that's tough on audio. The top half of the equation essentially calculates the total resistance, right?
Yes. It takes the circumference of the screw, multiplies it by the friction tax mu, and then subtracts the mechanical advantage of the thread pitch. It quantifies exactly how much the microscopic roughness of the steel is physically fighting your push.
And the denominator of that equation divides that massive resistance by the mechanical advantage of your lever arm. What the math proves is that moving a 10,000-pound load horizontally with a hand crank is entirely feasible, but it requires a very long lever arm, a very fine screw pitch, and an enormous amount of rotations to cover a short linear distance.
You are basically trading distance and time for the ability to overcome the friction coefficient.
Okay, so we have conquered the horizontal plane. The linear rail is sized, the wheels are specified, and the hand force is mathematically mapped. But the scenario parameters shift drastically right here. The exact same custom gear train now has to raise that 5-ton equipment vertically.
Vertical lift.
Yeah. The ground is no longer supporting the weight. Gravity takes over entirely. A simple screw and a long hand crank just aren't going to cut it when we need immense, concentrated rotational torque to lift 5 tons straight up.
No, elevating a load changes the fundamental physics of the entire problem. A standard parallel axis gearbox transmits its entire twisting force through a single pair of meshing gear teeth at any given microsecond.
Just one tooth at a time.
Exactly. And if you push 5 tons of vertical load through a single involute tooth, the shear forces will just snap it cleanly off the shaft. We need a mechanism that divides and conquers the load. We have to transition to epicyclic gearing, which is almost universally known as planetary gear trains.
Planetary gears are the undeniable champions of high-torque lifting applications. I mean, they give us massive mechanical advantage in a remarkably tight physical envelope. But it's the load distribution that really saves us, isn't it?
The load distribution is the absolute secret to their strength. Let's visualize the architecture for the listeners. At the absolute center of the mechanism is the sun gear. Meshing with the sun gear and physically orbiting around it are multiple planet gears, usually 3 or 4 of them.
Just like a solar system.
Exactly like a solar system. These planets are rigidly held in their orbits by a framework known as the carrier. And finally, wrapping around the entire assembly with its teeth facing inward is the internal ring gear.
So because we have 3 or 4 planet gears actively meshing with the sun gear simultaneously, the 5-ton load is divided into 3 or 4 separate paths. We are cutting the shear stress on any individual tooth by a massive margin.
A massive margin. The power density is totally unmatched, but the secondary benefit is the massive reduction ratios you can achieve by locking different components in place.
How does that work?
Well, if you hold the ring gear completely stationary and you drive the sun gear, the planets are forced to walk around the inside of the ring, slowly turning the carrier. A simple, single-stage planetary gear set can easily hit reduction ratios between 4-to-1 and 10-to-1.
And if 10-to-1 isn't enough torque to lift the load, the source nodes, we can compound them, right? We can stack a double reduction planetary set and multiply the advantage, hitting ratios anywhere from 10-to-1 all the way up to an astonishing 75-to-1.
Yes, 75-to-1. The input shaft spins 75 times just to turn the output shaft once, which multiplies the hand crank torque to absolutely Herculean levels.
So the math allows us to lift the load effortlessly. But lifting 5 tons vertically introduces a terrifying safety dynamic that horizontal motion does not possess at all.
It really does.
Let me push back on the safety aspect here. Because if I'm the operator, and I am relying on a 75-to-1 planetary gear reduction to inch 5 tons into the air, what happens if my hand slips? What happens if the input torque vanishes instantly? Does the load just plummet, spinning the gears backward until it hits the floor?
Yeah, that catastrophic event is known as backdriving, and it's terrifying. When you are lifting, the hand crank is the driver and the equipment is the driven load. But the moment you let go, gravity instantly turns the massive heavy equipment into the driver.
It reverses the roles.
Instantly. The immense potential energy of the suspended load forces the gear train to run in reverse. Without intervention, yes, the equipment would accelerate toward the ground, violently overspeeding the gearbox until it either disintegrated or the load impacted the floor.
You could, I don't know, slap a massive hydraulic brake caliper on the shaft.
You could, but external brakes can fail, pads can glaze over, and hydraulic fluid can leak. The sources provide a purely mechanical internal failsafe to stop backdriving instantly.
And what is that?
We integrate a self-locking worm gear directly into the lifting transmission.
Okay, a worm gear.
Right. A worm gear consists of a screw, the worm meshing perpendicularly with a standard spur-style gear. When the operator turns the hand crank, the screw easily rotates the gear, lifting the load. But the geometry of a worm gear can be specifically manipulated to create a one-way street for kinetic energy.
It basically acts as an automatic mechanical brake. Explain the physics of how a simple gear acts as a dead stop against 5 tons of gravity.
It all comes down to the relationship between the lead angle of the screw thread and the friction angle of the steel. If you engineer the worm with a very low lead angle, meaning the threads are very shallow and closely packed together, the system becomes self-locking.
Okay, shallow threads.
Right. So when gravity pulls on the heavy equipment, the gear tries to force the worm screw to spin backwards. But because the lead angle is so incredibly shallow, the rotational force is directed almost entirely sideways into the flanks of the screw thread rather than smoothly along its spiraling path.
So the friction angle overpowers the kinetic force. The steel teeth literally physically bind against the shallow pitch of the screw.
Exactly. It is physically impossible for the gear to turn the worm in that direction. If your hand slips off the crank, the load drops perhaps a millimeter before the gear teeth lock solid against the screw, suspending the 5 tons effortlessly in midair.
That is brilliant fail-safe kinematics. However, as we know, engineering always demands a sacrifice. You do not get a self-locking gravity brake without paying a severe mechanical toll. First, a worm gear forces a crossed-axis shaft arrangement, which fundamentally changes the layout of the gearbox. More importantly, worm gears are brutally inefficient.
They are notoriously inefficient.
Because they rely heavily on sliding friction rather than the smooth, rolling, conjugated action of our planetary gears we talked about earlier. The teeth of the gear are physically scraping along the coil of the worm under immense pressure.
Yes, and that sliding friction annihilates input energy, converting it directly into massive, massive amounts of heat. In a heavily loaded lifting scenario like this, The friction between the worm and the gear can spike the temperature so rapidly that the lubricating oil actually vaporizes.
And once the oil is gone,
Once the oil film collapses, the metal surfaces gall. They microscopically weld together and tear apart until the gear is utterly destroyed.
so how do we maintain the self-locking safety of the worm gear without letting the sliding friction melt the transmission into slag? Because the sources describe an incredibly elegant fluid dynamic solution to this exact problem, the hydrostatic worm gear bearing.
It's an amazing solution. Standard splash lubrication relies on the gears just dragging oil up from a sump. But in a hydrostatic setup, we completely abandon passive lubrication. We use an external pump to force high-pressure oil directly into the mesh point between the gear teeth and the worm coil.
So we're forcing it in.
Right. And the hydraulic pressure of the oil is mathematically calculated to be greater than the mechanical crushing force of the 5-ton load.
Wait, really? So the metal teeth never actually touch?
Never. The high-pressure fluid physically pries the steel surfaces apart. The gear is literally surfing on a microscopic, constantly renewed wave of pressurized oil.
That is incredible. So the sliding friction drops to near zero, completely eliminating the heat generation while perfectly preserving the self-locking geometry.
Exactly. Furthermore, the immense load tries to shove the worm screw violently sideways out of the casing, which is an axial thrust load. To counteract this, the system pumps high-pressure oil into a counterforce hydrostatic bearing at the far end of the worm shaft.
So the hydraulic pressure pushes back precisely as hard as the mechanical thrust is pushing forward. The entire heavy-duty worm shaft just flips effortlessly between cushions of pressurized oil.
It's perfectly balanced.
Okay, we have perfectly engineered the horizontal rail movement, and we have mastered the vertical lift with self-locking hydrostatically cooled safety. The final parameter of our custom project demands that we lift a massive plug and then precisely rotate it index at exactly 90 degrees out of the way.
Right indexing. When a scenario requires intermittent, highly precise fractional rotary motion, the undisputed standard is the Geneva wheel mechanism. We are no longer dealing with continuous rotation here. We are dealing with kinetic start and stop indexing.
For the listener trying to visualize this, a Geneva wheel operates a bit like a mechanical deadbolt. We have a continuously spinning driver wheel connected to our motor. Sitting right next to it is the driven wheel, which is connected to our massive plug. The driven wheel looks sort of like a cross, featuring 4 deep, straight slots cut into its face, spaced exactly 90 degrees apart.
Right, and attached to the face of the constantly spinning driver is a single heavy-duty roller pin. For 3/4 of its rotation, the driver spins completely freely and the pin touches nothing.
It's just spinning in the air.
Exactly. But once per revolution, the roller pin sweeps directly into one of the radial slots on the stationary driven wheel. As the driver continues its arc, the pin forces the slot sideways, rotating the driven wheel exactly 90 degrees. As the driver completes its sweep, the pin smoothly exits the slot, leaving the driven wheel at rest in its new position.
It perfectly converts continuous rotary motion into a perfect 1/4 turn. But if we are swinging a massive, heavy plug, it has momentum. When the pin exits the slot, what prevents the plug from simply coasting past the 90-degree mark, ruining the alignment entirely?
The genius of the Geneva design lies in the geometry of the lock, which functions exactly like that mechanical deadbolt you mentioned. If you examine the center of the spinning driver wheel, there is a raised, circular, concentric boss. And if you look at the driven wheel, between every single slot, the edge of the metal is cut out in a perfectly matched concave curve.
So as the roller pin leaves the slot, the solid circular edge of the spinning driver perfectly fills the concave cutout of the driven wheel.
You've got it. The solid metal boss of the driver slides right into the curved recess of the driven wheel, acting as a physical, unyielding block. The driven wheel is locked rigidly in place, physically incapable of rotating even a fraction of a millimeter. It holds that massive plug perfectly aligned while the roller pin travels its long, empty orbit, just waiting to engage the next slot.
And the transition between moving and locking is incredibly smooth. The source data points out a critical geometric rule. The radial slots on the driven wheel must be perfectly tangent to the circular path of the driving roller at the exact millisecond the roller enters and leaves the slot.
Tangency is key there. That tangency ensures the entry angle is precisely 90 degrees. Because of that specific geometry, the massive plug is started from a state of complete rest gradually. The acceleration curve peaks smoothly, and then the momentum is gradually checked, bringing the mass to a smooth, incredibly controlled halt.
No violent shock loading.
None. No slamming of gears is pure kinematic poetry.
But let's say the project requirements shift a bit. Let's say we don't want a continuously spinning motor running a mechanical Geneva wheel. We want to automate the plug rotation electrically. What are the engineering options for high-torque electrical indexing?
When automation dictates the design, we usually transition to rotary actuators. The sources specifically highlight rotary solenoids for these applications. They are astonishingly power dense. I mean, a rotary solenoid less than 2¼ inches long can instantly generate well over 100 pound-force inches of rotational torque.
Wait, really? That is an immense amount of twisting force from a component the size of, like, a D-cell battery.
It's massive.
The physics behind that power density must rely entirely on advanced electromagnetism.
It does. The actuator leverages the brutal, instantaneous force of magnetic attraction and repulsion. Inside the actuator, the electromagnetic flux generated by the solenoid coil violently interacts with the permanent magnetic field of a neodymium iron disk magnet mounted directly to the armature.
So when you pulse the coil,
When you pulse the coil with current, the interacting magnetic fields snap the armature through a precise, heavy-duty arc, instantly rotating the plug.
the power is incredible, but doesn't that introduce a severe vulnerability? I mean, if we are firing an actuator as over 100 pound-force inches of instant torque, or we're driving the system with an electric motor, what happens if something goes wrong? What happens if someone drops a wrench in the mechanism or the heavy plug physically jams against the casing?
That's a huge problem. In a rigid drive system, a jammed plug means the kinetic energy has absolutely nowhere to go. The electric motor continues to pour massive torque into the stationary shaft until the weakest point fails. The motor windings will burn out, or worse, the sheer twisting force just snaps the hardened steel drive shaft in half like a dry twig.
Which is why a robust system relies on an overload relief clutch, right? It basically functions as a mechanical circuit breaker, a protective fuse designed to safely slip rather than violently snap.
Exactly. The most reliable architecture for this is the double plate friction coupling with spring loading. We take the drive shaft coming from the motor. Mounted to it is a heavy steel collar featuring slotted plates. We sandwich high-performance friction discs between these plates. The sources highlight the use of phenolic laminate for these specific discs.
Phenolic laminate is crucial here, isn't it? If we use steel friction discs against a steel gear, they would just instantly gall and weld together under the high heat. Phenolic laminate is a high-tech, heat-resistant plastic composite. It degrades gracefully under extreme friction, maintaining its grip without destroying the mating metal surfaces.
It's the perfect material for a mechanical fuse. So the gear that actually connects to the massive plug is sandwiched perfectly tightly between these phenolic discs. Heavy-duty coil springs compress the entire assembly. Under normal, safe operating conditions, the spring pressure creates so much friction that the shaft, the phenolic discs, and the gear all rotate together as one solid, unified mass.
But the moment the plug hits an obstruction and jams,
The gear stops dead. The electric motor, however, continues to drive the shaft with immense force. Because the gear is not keyed or pinned directly to the shaft, it is held solely by the friction of the phenolic sandwich. The immense building torque of the jammed motor finally exceeds the friction coefficient of the springs. The mechanical fuse blows.
the phenolic laminate discs begin to smoothly slip against the faces of the jammed gear.
Yes, the motor spins happily, the shaft rotates, and the phenolic discs just slide right over the stationary gear face. The kinetic energy is converted safely into heat rather than destructive shear force. The motor is completely protected, the drive shaft remains intact, and the heavy plug just sits safely jammed until an operator can come clear the obstruction.
Fantastic. We have successfully engineered the entire system. The linear horizontal force is mathematically verified. The vertical lift is secure with planetary reduction and hydrostatically cooled self-locking worm gears. The heavy plug indexing is protected by phenolic friction clutches. I mean, the CAD files look perfect.
CAD files always look perfect,
Yeah.
but mathematics operates in a vacuum. A perfect theoretical design can be utterly destroyed in a matter of hours by a microscopic installation error or a hostile external environment.
Which transitions us perfectly into the masterclass section. We are taking the engineering off the paper and throwing it into the chaotic reality of the physical world.
Nice.
Let's diagnose the most common catastrophic failures engineers actually ask about online. Here is online question number 1. I designed a high-performance aerospace gearbox. Everything was mathematically verified. The gears were cut to absolute precision. But during the very first full load test, within minutes, the gears scored. The metal tore off the teeth. Why?
Ah. When mathematically perfect gears destroy themselves instantly on the test stand, the root cause is almost always manufacturing or assembly errors regarding the casing itself.
Not the gears.
Not the gears. Aerospace gearboxes require extremely lightweight, thin-walled aluminum or magnesium casings to save weight. When the assembly mechanic bolted the two halves of that lightweight casing together, they almost certainly tightened all the bolts down the left side first and then moved to the right side.
Instead of using a crisscross star pattern to distribute the clamping force evenly.
Exactly. Tightening one side of a thin-walled casing first causes the entire metal structure to bow and warp on a microscopic level. That invisible bow misaligns the bearing bores, so when the perfectly cut gears are dropped into the warped casing, their shafts are no longer perfectly parallel.
So the gears are meshing at a microscopic angle. The involute curve we talked about earlier relies on the load being spread evenly across the entire face width of the tooth. But because of the warped casing, the entire load is concentrated on the very outer edge of the gear teeth.
Yes. That phenomenon is called edge loading. The immense, concentrated stress instantly vaporizes the microscopic film of lubricating oil. The steel violently rubs against steel, tearing the crystalline structure apart. The gear teeth score and shred themselves in literally minutes. The failure wasn't the gear design. The failure was the sequence of a mechanic's wrench.
That is brutal. It proves that $1 million design is entirely at the mercy of the final assembly process. Let's look at online question number 2. I completely rebuilt a heavy industrial gearbox. I spared no expense. I even performed a high-temperature hot oil flush before startup to ensure the internal plumbing was surgically clean. But the moment I brought it up to operating speed, the high-speed pinion bearing seized and shattered. What went wrong?
Well, the engineer correctly identified the need for cleanliness, but they committed a fatal environmental installation error regarding the plumbing hierarchy. Let's assume this industrial gearbox is installed at a desert solar facility, or perhaps a high particulate mining operation.
Lots of dust.
Tons of dust. During the rebuild, the external oil pipes connecting the massive oil filter to the gear unit were disconnected and left sitting on a workbench for, say, an hour.
During which time, ambient dust, silica sand, or metallic debris just settled inside the open pipes.
Right. And the engineer assumed the hot oil flush would solve everything. But if the debris settled in the specific pipe that connects the output of the oil filter directly to the input of the gearbox, what we call the downstream plumbing, the filter is entirely bypassed.
Because the filter can only clean the oil before it enters that final pipe. By leaving the downstream pipe open on the bench, they essentially loaded a shotgun with silica sand.
Exactly. When they activated the high-pressure hot oil flush, it didn't clean the system. It acted as a high-speed delivery mechanism, injecting a slurry of pure silica sand directly into the ultra-tight clearances of the high-speed pinion bearing. The microscopic rollers seized instantly under the friction, shattering the bearing cage and utterly destroying the gearbox. The unit died because a single piece of pipe wasn't capped with a 50-cent plastic plug while resting on a bench.
The details absolutely dictate survival. Let's move to online question number 3. My gearbox is running incredibly rough, and the internal temperature is skyrocketing. I've verified my thermal ratings, and the cast iron casing is mathematically large enough to dissipate the heat generated by the internal friction. The splash lubrication is verified. Why is it melting down?
This is a classic issue. If the internal math for heat generation and surface area dissipation is strictly correct, the failure is occurring on the outside of the casing. A gearbox isn't just a structural container, it acts as a massive thermal radiator. It absorbs the internal heat of the friction and radiates it out into the surrounding ambient air.
But what if the air can't get to it?
Right. If this gearbox is operating in a cement plant, a paper mill, or a coal processing facility, a thick layer of fly ash, wood pulp, or industrial dirt will rapidly settle on the exterior of the casing.
And that thick layer of environmental debris basically acts as an incredibly efficient thermal blanket. It insulates the cast iron, physically trapping the heat inside the metal.
Yes. The casing can no longer breathe. The internal temperature of the lubricating oil begins to climb exponentially. As oil heats up, its viscosity plummets. It thins out until it flows like water. The oil film becomes too thin to physically separate the microscopic peaks and valleys of the gear teeth. The metal grinds directly against metal, which causes the rough running noise and generates even more heat in a catastrophic feedback loop until the bearings just melt.
To give the listeners a sense of the sheer volume of heat we're actually dealing with, the sources provide a baseline engineering rule of thumb for cooling heavily loaded industrial gears.
They do. The thermal physics dictate that it takes approximately 1 gallon or roughly 4 liters of oil circulating per minute just to remove the thermal energy developed by a 400 horsepower load.
That's a massive amount of fluid just for cooling.
It is. If that massive amount of thermal energy cannot radiate through the casing because it's buried under a half-inch of fly ash, the system will rapidly self-destruct.
Which brings us to the final real-world failure mode. Online question number 4. I calculated the bending stress at the root of my gear teeth perfectly. The material is correct, the lubrication is flawless, and the casing is clean. Yet after 3 months of operation, the gear teeth are developing fatigue cracks at the root and violently snapping off the shaft. Why?
When gear teeth snap cleanly off at the root despite perfect mathematical stress calculations, the diagnosis almost always points to severe misalignment and base pitch issues. The physical base pitch of the driving gear must exactly match the base pitch of the driven gear. If there is a microscopic deviation, perhaps a fraction of a thousandth of an inch difference due to manufacturing tolerances, the teeth do not enter the mesh smoothly.
Instead of the involute curve rolling flawlessly, one tooth arrives early or late, violently slamming into the mating tooth to force the rotation.
Exactly. That microscopic slamming creates intense high-frequency vibration and completely improper load sharing. The teeth are hammered thousands of times a minute. That relentless hammering initiates microscopic fatigue cracks at the root of the tooth, which just propagate through the steel until the entire tooth snaps off.
But the base pitch can be altered by external physical forces, not just bad manufacturing, right? Our sources highlight the danger of overhung loads.
An overhung load is a massive external threat. If the operator attaches a heavy drive belt pulley, a massive sprocket, or a large propeller directly to the output shaft of the gearbox without independent support, the immense weight and tension of that attachment physically pulls the steel shaft sideways.
It essentially acts as a lever, physically bending the shaft inside the gearbox.
And when the shaft bends, the gear mounted on that shaft tilts. The gears are no longer running parallel. The base pitch geometry is destroyed, edge loading occurs just like with the warped casing, and the teeth are hammered until they snap. Any heavy external load must be supported independently by external pillow block bearings to isolate the gearbox shaft from those bending forces.
We also have to address how the environment degrades the material itself, fundamentally weakening the root of the tooth before the loads even apply.
Environmental moisture is an absolute gear killer. Consider a food processing plant where the machinery is subjected to high-pressure, caustic chemical washdowns every single shift. If the engineer specified standard porous cast iron housings and basic carbon steel breather vents, that high-pressure moisture will just bypass the seals.
And get inside.
Yes. The water condenses inside the gearbox, heavily rusting the steel shafts and actively attacking the root of the gear teeth.
The rust acts as a stress concentrator, pre-weakening the tooth structure so it snaps under normal operating loads. The engineering solution requires specifying specialized epoxy coatings for the casing, heavy-duty labyrinth seals for the shafts, and full stainless steel hardware to survive the chemical onslaught. It highlights how much of mechanical engineering is simply building fortresses to protect your perfect internal math from a hostile external world.
That's a great way to put it. The kinematic math is totally predictable. Defending that mathematics from human installation errors, thermal blankets, and caustic environments, that is the true masterclass of mechanical design.
This has been an incredibly deep, relentless dive into custom motion control. We've built an entire custom transmission on our mental workbench. We've explored the metallurgy of track wheels, the friction taxes of horizontal hand forces, the incredible load-sharing capabilities of planetary gears, the fluid dynamics of hydrostatic worm bearings, and the mechanical deadbolts of Geneva indexing. We've even diagnosed the real-world disasters that destroy perfect designs. But before we wrap up this session, we need to leave the listener with a final, mind-bending mechanical concept from the furthest edges of the source data, something they can map out in their heads long after the audio stops.
Oh, I know exactly what you're talking about. If we want to look at the absolute extremes of kinematic mathematics, we have to explore a configuration known as Ferguson's paradox. It is the driving geometry behind what engineers call the phantom drive reverted compound train.
A phantom drive. The name alone sounds like it defies the laws of physics. Let's walk the listener visually through the mechanics of this paradox. How do we even build it?
We return to the architecture of the planetary gear train we used for the lifting mechanism. But instead of a single sun gear in the center, we stack 3 separate sun gears side by side on the exact same central axis. Meshing with all three of these sun gears simultaneously is a single extra-long planet gear sweeping around the orbit.
Okay, I see it. 3 sun gears in the center, one long planet rolling across all of them at once. In a normal setup, if the planet sweeps around, all 3 sun gears should rotate at the exact same speed.
They should if they all had the exact same number of teeth. But Ferguson's paradox relies on altering the tooth counts by the smallest possible margin. We give the first sun gear exactly 100 teeth. We give the second sun gear 99 teeth. And we give the third sun gear 101 teeth.
Wait, so the planet gear, which has a constant number of teeth, is simultaneously meshing with 100 teeth, 99 teeth, and 101 teeth as it orbits. How does the Mac resolve that physical impossibility?
The kinematics resolve it by forcing the output gears into entirely contradictory motion. When you spin the input, driving the planet gear around its orbit, the first sun gear with 100 teeth behaves normally. It provides a standard, predictable forward rotation. But the sun gear with 99 teeth has slightly less circumference. For the planet gear to mesh with it during the constant orbit, it physically pushes the 99-tooth gear forward faster than the baseline.
In the gear with 101 teeth.
It has too much circumference for the baseline orbit. So to maintain the mesh, the orbiting planet gear physically drags the 101-tooth gear backward.
So from a single, continuously spinning input planet, you have one output gear spinning forward and an identical-looking gear directly next to it spinning backward. But where's the phantom motion? Where's the paradox?
The paradox deepens when you manipulate the ratios to their absolute mathematical limit. By carefully selecting the pitch and the planetary orbit, you can engineer a ratio where the forward push of the orbit perfectly mathematically cancels out the backward drag of the tooth count. The result is an output gear that is fully meshed with a furiously spinning planet, yet it has exactly 0 angular velocity.
It sits completely dead still while the mechanical universe spins violently around it.
It remains perfectly stationary. It looks like an impossible optical illusion, a broken piece of physics, but it is pure, undeniable kinematics. It is the ultimate reminder that in gear design, you aren't just moving metal, you're organizing mathematics. And if you organize the math in highly specific ways, the gear train will fight itself to a perfect stationary standstill.
That is phenomenal. An entire transmission mathematically canceling its own kinetic energy to achieve perfect stillness. It proves that whether you are dealing with a 5-ton vertical lift or a phantom drive, the geometry really rules everything. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.